Getting there. Voila! According to some clock, it is 10 a.m. and Rob 101 is ready to go. Good morning. We're 2 months into the term. University of Michigan hasn't been canceled from the face of the earth. Undergraduates are under lockdown. They've got 8 more days, then they're free. Don't party too hard, they'll lock you down again. Okay, easy for me to make fun of it. I'm not locked down, okay? So we're looking at something called the dot product and all the cool things that gives us in Rn, the notion of orthogonal vectors, and how to take a set of vectors that is not necessarily orthogonal and turn it into a set that is orthogonal. The process that does that is called Gram-Schmidt, and you can derive it if you forget it just by writing down a linear combination of u1 and u2 and making it orthogonal to the first vector u1, and you will pick up this first coefficient with, whoops, I guess, yep, this will be the first coefficient. You'll pick that up right away. So I never memorize Gram-Schmidt. I forget it sometimes, and I just rederive it quickly. So the assumption it makes is that you start out with a set of vectors that's linearly independent, and the basic Gram-Schmidt does not normalize as you go because it's designed for hand calculations, okay? In Julia or MATLAB or any other program, I tend to normalize as I go, and then I don't need these because they're automatically 1. So I'll just add one other step. VK equals VK divided by norm of VK, and then I loop. Okay, so that's what I do. Now the key thing is if these are linearly independent, then these are going to be linearly independent, hence none of them are 0, and you're never dividing by 0. That's while we're waiting for everybody to really get fired up and your brain's going on a Monday morning, what do you think it means if I calculate this and what's left over is like super small, like 0, okay, numerically 0. What would that mean? Life is hard. I've got the blues. No, it would mean that you have 0 here and that UK is then linearly dependent. Whoops, I'm left off. V1, V2, VK minus 1, that was bad. It would mean that you have 0 here, then UK is linearly dependent on the previous ones, okay? So that means this set is not linearly independent. So if you're really doing Gram-Schmidt, do you ever check this? No. Just go in, and if the norm of this thing is small, throw it away, and then loop through and then keep building your vectors, okay? So we'll have you do that in the homework. It's an easy way to check for linear independence, and it's another way to count the number of linearly independent vectors, okay? So you just run Gram-Schmidt. Oops, I got something too small. It's 10 to the minus 8 in norm. I'm going to call that 0. And then I would throw out this vector from my set and just move on to the next one, reindex, go forward, okay? So I'll leave that as a friendly amendment to Gram-Schmidt. But the basic one assumes linear independence. That way this can never be 0. You're never dividing by 0 when you normalize, etc. So what I do is I put in a little test and I just check because I don't believe. Okay. So once you have that, and you have that somebody has given you the notion of a orthonormal matrix, which doesn't have to be square, and we just do Q transpose times Q, we get a square matrix that's equal to the identity. So technically that's a left inverse, but we don't do left inverses in Rob 1, so it's just Q transpose times Q is the identity. You can show that any matrix whose columns are linearly independent can be factored as an orthonormal matrix times an upper triangular matrix, and it's called the QR factorization. And then R will be square equal to the number of columns in A, same as the number of columns in Q, and its determinant will be non-zero. In fact, when A is square, the determinant is non-zero always, and if A is square, then the determinant of R is plus or minus the determinant of A. But that's a small detail we don't care too much about. Okay, so we just call the columns of A, we apply Gram-Schmidt, we normalize. These are now orthonormal vectors, and Q is an orthonormal matrix. And then we can use this for solving AX equals B when the columns of A are linearly independent, so the rank is full. And there's two cases we can look at. We can look at B in the range of A, which is the same as B is a linear combination of the columns of A. And then AX equals B if and only if QX equals B, but I can multiply by Q transpose on both sides, and I have RX equals Q transpose B. And this is what we would suggest you solve, because we don't like inverting matrices, but that's the answer. And then the fun thing that happens is if B is not in the range of A, we do a least squares solution. So we define X star is argmin, so it's the X that minimizes AX minus B in norm. And whether you're minimizing the norm or the norm squared or the norm to the fourth power or the norm to any power greater than 1 doesn't change the minimizing vector. So square is often nice. And so that's called the least squares solution. And it satisfies, remember, we multiply just both sides of the equation by A transpose. It's kind of magic. And then you plug in and you work out what A transpose A is, you're down to solving the exact same equation as when you have a perfect solution. The difference is, there should be a star here. The only difference is, in this case, the error is 0, AX minus B is 0, and then in this case, AX star minus B is not 0. Okay, so that's the only difference. Okay, cool. Equation has a solution, it's not even square, we're really good with that. QR factorization, boom. Equation is rectangular, B is not in the range of A, it doesn't have a solution, that's our basic regression. And so I thought I would go back to day 1 of Rob 101. Ooh. Now, we didn't write things in matrices on day 1. We got there by day 2 or 3 or something, okay? Even I don't remember. But these are the 3 examples that we worked. We worked them out long way, X plus Y, and did all the substitutions just like we would have in high school, okay? So we did our high school algebra. We worked this one out, it has no solution. Well, you can check, okay, B is not a linear combination of the columns of A, but we know how to handle it, least squares. We can check this one. We did in class, we found a solution, had a unique solution. And then we had this case where you can see B is a linear combination of the columns of A because it really is one of the columns of A, but we weren't sophisticated to make that observation on day 1 in Rob 101. Okay, but you can check the determinant here, that's -6. And then minus that gives 0. So there's actually an infinite number of solutions. And so that's the only case that we haven't cleaned up. We've cleaned up everything. We did square equations, that's no problem for us. We've done rectangular equations, has a solution, doesn't have a solution. We do approximate solutions. We've got everything cleaned up except for this one case. So how to handle AX equals B when it has an infinite number of solutions. We're going to wrap it up. That's the end of chapter 9, and then we're going to do some really cool stuff. So this is, not that this isn't cool, okay, this is actually pretty cool, and I'm going to give an example of how that works on Cassie. Okay, so we're going to look at AX equals B. We'll do the rectangular case, A equals N by M. and we suppose it has a solution, so B is an element of the range of A. So B is a linear combination of the columns of A, and we know that's if and only if a solution exists. Okay, so that's cool. You have to admit, we've gotten pretty sophisticated about linear systems of equation. We can write down very compactly conditions for existence. We understand exactly what's going on. So it has a solution, so let's let x bar be a solution. We haven't said anything yet that it's unique, and you know I want to handle the case it's not unique, so that's why I'm saying a solution and not the solution. And all that means is A times x bar equals B. Okay. So now let's define the null space of A. That's going to be all vectors in Rm, A is n by m, that get mapped into 0 when you apply A to it. Okay. So the solution of AX equals B is unique if and only if the null space is equal to the 0 vector. Looks like an O. Try to make it a 0. I don't know how to make it any different. There's a 0. It's the 0 vector in Rm. Okay? Now, that's not the way we've normally said uniqueness. Our normal way of talking about uniqueness was the columns of A are linearly independent. But by the rank plus nullity theorem, see if the null of A is equal to the 0 vector, the dimension of the null space is 0. So the nullity of A is 0. And that's if and only if the rank of A equals m, the number of columns. Okay. Now why do I want the null space to appear? Because let's note. I take x tilde in the null space of A, then x bar plus x tilde is still a solution of the equation. We'll show that. Okay, I'll write this down and then we will catch our breath. I can see you're writing furiously. Okay, let's catch our breath. Whew. We're all excited. We're taking care of the very last case that we discovered on day 1 in the course. Okay, we have a solution exists. We've got one of them. We just called it x bar. You want to call it x triple bar? I don't care. We look at all of the solutions that get mapped into 0, and the only way we get a non-trivial solution is if the columns of A are linearly dependent, okay? So if the columns of A are linearly dependent, we get a non-trivial null space. So if we have x tilde in the null space, so meaning that the columns of A are not linearly independent, x tilde is not 0, I claim that's still a solution. And the reason is, if I go A times x bar plus x tilde, that's A times x bar plus a times x tilde. Well, x tilde is in the null space. That's 0. And a times x bar is b. Okay, so the question becomes, if the nullity of A is bigger than 0, how to choose among all of the solutions to AX equals B. There's an infinite number of them. Okay. I solve the equation, I get this one. Tribby, she happened to pull a different solution. And what we'll have is that her solution and my solution differs by an element of the null space of A. Whose solution do you want to like best? Tribby's solution? My solution? What's the criteria to search among all of these solutions and choose one? So this is the suggestion. We'll let x star equals the arg min of the norm of x over all solutions to the equation. Okay, let's make sure we understand what this means. And then let me write down one line before we talk, because the way you'll often see this is the norm squared. Okay, so what is this problem saying? It's saying we're going to look at all of the solutions to the equation. There's an infinite number of them. How do we sort through and find one that appeals to us? And what we're going to say is we're going to take that solution which has the smallest norm, and that's the same thing as saying it has the smallest norm squared. So people like to talk about least squares problem, not least square root of squares problems, okay? So that's why we do that, the least squares. So let's look at all of the solutions. So among all solutions, choose the one of least squared norm. Okay, so this is a constrained optimization problem. It's a little bit different than we did before. Before we minimized ax minus b squared, and we looked over all possible x's in Rm. Now we're not looking over all possible x's in Rm, we're only looking at x's that satisfy the equation. So this is called a constraint. Okay, so it's a constrained optimization problem. Minimize norm of x squared subject to ax equals b. And ax equals b is a constraint on X an element of Rm. So it's kind of cool. It's a little bit different than our least squares solution. Where, yep, you want the smallest norm, but 0 is of no interest to us because it is not necessarily a solution of this equation. Now, if b is 0, then it is 0, and there's nothing interesting going on. But if b is not 0, then x equals 0 is not of interest to us, okay? So we want to look at all the possible x's such that the equation is satisfied. Okay, and then we can solve that problem. The details are in the book of why even this is true. But the theorem is, suppose the columns of A transpose are linearly independent. Then blah, 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 and I will write that down in a second. Okay, everybody sees A, it has rows. When we transpose it, they become the columns of A transpose. So when I say the columns of A transpose are linearly independent, what am I really saying? The rows of A are linearly independent, okay? It's the same thing. It's just that we haven't talked about row vectors being linearly independent. You can extend all that stuff, but it's really saying the rows of A are linearly independent. The same thing, but because we've worked with columns of matrices being vectors in Rm or Rn, depending upon our sizes, etc., I'm stating it as the columns of A transpose are linearly independent. Okay. Then, too big. X star equals arg min norm x squared, subject to, it's a solution of the equation, if and only if, and that's the cool thing. And it looks similar to our least squares solution. You get A transpose dot times A transpose inverse times B. Okay, so it's a little bit like it. Remember the least squares? There was an A transpose here, and these two guys were swapped. That's what the least squares look like. You can go back and look. Okay. But the way I prefer us to think about this is we write X star equals A transpose times alpha. And then we have A times A transpose alpha equals B. So you solve this one first and this one second. Right, because I'm trying to help you develop an aversion for the matrix inverse, okay? Just because in practice it's not a good thing to do. So this is a way to write down the equation where you don't have the matrix inverse. So, okay, so alpha is a vector in Rn here. Okay, now the book applies QR, and you can just see the book for that. So I'll let you do that on your own. Okay, now what the book doesn't have is a super cool example. Okay, so I figured, you can read this. So what's beautiful? Simple conditions on A, and you've got an explicit solution. And then once you get to here, you guys would kill that with LU, or you could kill that with QR, and then bingo, there's one more matrix multiplication, okay? So you can solve huge problems, and in optimization, we do that. So this is setting us up for chapter 11. We got chapter 10 to do in between, but here's one of these systems where we're doing AX equals B has an infinite number of solutions, and we're doing the minimum norm solution to it. How does it arise on a physical thing? Okay, so I'll post all this. I'm going to first think about a robot as an inverted pendulum, because when you're walking, your foot stays in place. Got a big mass here, relatively light legs, and then as you're walking, the center of mass is moving, and it looks like a pendulum that's rotating about the contact point. This is a normal pendulum. This is the inverted pendulum. We're good with that? There, so you guys somewhere heard some rumor that this guy Newton talked about F equals ma, so you've heard about forces someplace along the way, okay? And you also heard that for every action, there's an equal and opposite reaction, right? And when I was taught physics in those terms, I had no clue what was going on. It just seemed stupid, okay? When I learned some calculus, then it made sense. We don't do calculus, but anyway, so you can show that the forces acting on the center of mass of the robot are equal and opposite to the forces acting at the toe. Because robots, they don't have jet engines attached to them, so we're not applying forces at the center of mass directly. We're like humans, we apply forces on the ground and push backwards that propels us forward, okay? So fundamentally, when you're wanting to keep a robot upright, you need to keep this force counteracting gravity, but not too much that you're jumping in the air, so it's a delicate thing. And this force you're doing to propel the speed, the acceleration of going forward, okay? So that's really what you're doing. So you're generating forces. Now where they come from is you have joints in the robot. So here's a knee, here's a hip. This is a planar look at it, the very first robot I worked on. It has 4 motors. And when you look at this diagram, you think that that's a motor at the knee, but it's not. It's called a harmonic drive. It's a 50-to-1 gear ratio. The motor is actually up here, and it's connected down there by what's called a timing belt. It's got little teeth in the belt, and the pulley has little teeth in it, so there's no slipping. And as the motor turns, the gear turns, and then this thing turns 50 times before this thing would turn once, okay? That's a gear ratio. But anyway, we're generating torques at the joints via the motors on the robot. So that's Rabbit. Here's Cassie. You look underneath all of these shells. Cassie's really cute. This thing is a motor and a harmonic drive, and they're now really small, okay? This is 15 years later between Rabbit and Cassie, okay? They're now really compact. When you break down where all the motors and what they're doing, there's a motor at the top that allows the leg to twist. There's a motor that allows the leg to go out and a motor that allows the leg to go forward. And then Cassie is modeled on a bird called a cassowary, which is like an ostrich. It's really bizarre, right? You see how the knees are pointed backwards from yours and mine? The cassowary thinks your knees are in the wrong direction, okay? So that's what Cassie is modeled on. It's not me, Jonathan Hurst, and he and I have a really long, very positive history. I discovered him as a grad student at Carnegie Mellon, and we started working together, even though I was a professor and he was a student. It was a brilliant relationship. But all of the green cans have motors. These things have springs. So there's some springiness built in. But you can see what's happening now. I'm trying to generate forces at the foot. And so Cassie, there's an X direction, a Y direction, and a Z direction. I've got 10 motors, okay? Yes, only 5 of them are on the ground, but when a leg is swinging forward, that causes reactions on the back one too, okay? And using Calc 3, I can derive a matrix that relates the torque at each of the 10 joints to the forces at the foot. Okay, so there's 10 torques to generate 3 forces. You get it? It's under-constrained. There's not a unique relationship between motor torques and forces on the ground. So what do? We choose the torque of smallest value. I just stack them up as a vector such that I meet the ground reaction forces I want to drive the robot forward, okay? Make sense? Now, torque squared you can relate to the current in the windings of the motor. And when you have current and resistance, that's called power loss. They heat up, okay? So keeping this small is reducing the instantaneous power also in the robot, which what? Makes my battery last longer. So this is like really smart to do. Ooh. So this is what you guys now know how to solve, okay? Most of my graduate students learn how to solve this equation about 4 months or 5 months into working with me, okay? My grad students, okay? You guys now can read the book and you can solve that. Now here's the physical reality though. When I calculate this, it could say the most efficient thing is to use most of the torque coming at the toe of the robot, for example. Well, that motor is really little, okay? Just like your ankle torque is not as big as the torque you can generate up at your hips, okay? So the reality is I want to put constraints on the torque that satisfy upper bounds and lower bounds. Ooh. So it's not just equality constraints, but I want to put inequality constraints on it. And this is called a quadratic program. When you minimize a quadratic quantity, it can be more general than that, subject to linear constraints and linear inequality constraints, it's called a QP for short. So this is Q is not for these orthonormal matrices and stuff, but it's Q for quadratic, which is very much related to orthogonal matrices, but it's called QP. So when you hear QP, it's cool. We are going to use QPs in project 3. So we'll get there, but that's where things are coming. We're going to use QPs to stabilize a Segway, keep it upright. And how you can do that, it doesn't look at all related, but that's what projects are about, is we give you tools and then we have you discover new ways to apply them, just like you're doing now with regression. Ooh, ah, okay. Not so much, got it. Okay. Okay, so I'll put in here, insert Cassie. And I'll do that before I post. Okay, so we're going to start chapter 10, and it's super cool. Solving nonlinear equations. Boom. So we've kind of killed linear equations. We kind of like know almost everything about them. There's a few other little subtleties that one can get into, but we've done a really fantastic job of solving linear equations. You guys know more than almost anybody on campus. Okay. Learning objectives. Chapter 10, learning objectives. done. Somehow you got in there. Okay. So even though this is a course on linear algebra, we're going to move on to nonlinear stuff. And the first things we do, you're going to say, well, it doesn't seem to be so related to linear algebra, and then that will be true. But I'm going to teach you something called the bisection algorithm, which is an easy way to solve for points. You give me a complicated function, f takes the reals to the reals. Cancel. And you want to solve f of x equals 0. I'll give you a simple way to do a boom, 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 and converge to the solution. It's really kind of fun, actually. So we're going to move from linear equations to nonlinear equations. Everything we do is going to be aimed at situations where there's not any way you can write down a closed form solution. So you guys, when you learned linear stuff, yes, you could grind it out and just write down an answer, this closed form. When you have a quadratic equation, you guys know the answer to it. There's actually formulas for cubic equations. There are formulas for quartic equations, and you can prove there is no general formula to find solutions of quintic and higher. It stops at 4. It's not that human beings are not smart enough to find the answer. Human beings are smart enough to prove there is no formula in this class of objects that will ever give you the roots of the equation. Okay? Closed form does not exist. The only way to get it is an algorithm that iterates, and it will not find it exactly, but it can get as close as an engineer wants to get, or an applied mathematician, or a physicist, etc. Okay, so we're going to do iterative solutions to nonlinear problems. Now, you guys have been doing for loops, and they tend to stop at 7 or 100 or 1,000, which is the size of the matrix. Here, we're going to go until we get close enough. Okay, so that's different. It's not for k equals 1 to 27. It's loop until the difference from f of x being 0 is close enough, and we said, okay, fine, we're down to 10 to the minus 8. That's our tolerance, okay? So that's what we're going to do. It's very different, but because you guys are good with looping, when I write down these things that iterate, you're going to go, oh, it looks like Gram-Schmidt, or it looks like back substitution. It's just that we don't stop anytime soon. We just keep on going, okay? The key thing is, well, I'm not assuming any calculus. So some of you I know have AP this, some of you are in differential equations this term, some of you in that. I'm going to pretend you do not know what a derivative is. We are not going to use analytical derivatives. I'm going to show you how to calculate derivatives numerically, and I'm going to tell you what a derivative is, even if you already know what a derivative is. So we're going to learn calculus from a different way. So if you don't know calculus, this course is setting you up for success in calculus. And those of you who already have calculus are going to go, huh, how come they didn't give me this background before I started learning calculus? It would have made a lot more sense. So that's what we're going to be doing. And so bisection, Newton, is going to come back, etc. We'll learn about linear approximations of nonlinear functions, and that's where our linear algebra is going to come back in to us. And there'll be really cool things like a Jacobian. Ooh, what is that? So there's a lot of cool stuff in this chapter, lots of graphs. I'll be plugging in a lot of graphs. It's a little bit irritating for you when I just, all of a sudden, my notes become 3 pages and you've only got 6 lines, I know. But I'm just giving you a heads up. You may want to have parts of the chapter beside you when we go. Ready? Excited? I'm excited. Okay. So let's start with some vocabulary. Isn't that the most exciting way to start? Oh, that hurts. Okay, so let's take a function from Rm into Rn, okay? So let that be a function. Now, to that function, I'm going to associate an equation. Okay. This is an equation because it has, yes, an equal sign, okay? That's what it means to be an equation. There's an equal sign. F is just a function that doesn't define an equation. So f of x equals 0 is an equation. A solution to f of x equals 0 is called a root. So in the book, I give you a little hint about the Arab origins of the word root. Okay, so a lot of our mathematics was discovered way back in medieval times, and it was not always the Greeks. It was not always what was going on in Europe. A lot of this stuff was happening in northern Africa. Okay, it's happening in the Arab world. Super cool scholars, and they're really into mathematics. Everybody cared about math because then they could build calendars, and they could make predictions about the seasons, and they could make all sorts of things that help make their economies work, okay? So math was important. Okay, so that's a solution to that is called a root. So what it means is x star is a root if and only if f of x star equals 0. Okay, so that's a root. Now, you might think setting it equal to 0 is extremely limiting. Why not set it equal to some other constant, okay? So suppose f of x equals c is the equation. For c, just some point in Rn, you know, a constant vector. Once again, you know, vocabulary, it's like going to the dentist, okay? And my wife hates it when I say that because she's the dean of the School of Dentistry, okay? So she better not watch this class video, okay? So is f of x star equal to c a root of the equation? Okay. Simple question. Yes, no. And the answer is no. Technically not, okay? So what do we do? It is a root of f bar of x equals 0, where f bar of x is by definition equal to f of x minus c. What am I doing? Okay, but, I'll just give you a clue. Most engineers could care less, okay? It's splitting hairs. It's so splitting hairs, so, but the only reason I'm pointing it out is eventually you guys are not going to want to write all of your code from scratch. You're going to want to use someone else's code, a package, okay, that has all the bells and whistles and every little numerical thing sweated out because that's their life's work, okay? And I spent 15 minutes in Rob 101 and I wrote my algorithm, okay? So they've really done it. They're going to set it up so that it solves the nominal problem. You want to solve this problem, fine. You just need to pass this function and then understand that you're getting the solution for that, okay? So that's the only reason we do it, okay? So most of the packages are set up to solve this equation and not that one, but it's a simple transformation. So don't worry about that. Now, so I said my function was taking Rm into Rn. So we are working with real numbers. It's my R. Okay, so I'm trying to get everything set up kind of firm so you guys don't feel like we're just hacking, because we're not going to be just hacking. I want to kind of make it seem solid what we're doing, working with real numbers. What does that mean? We're not doing complex numbers, right? So what about the equation x squared plus 1 equals 0? Does it have any roots? The answer is no, okay? So x squared plus 1 equals 0 if and only if x squared equals minus 1, if and only if imaginary answers are allowed, right? So that's the root of square root of minus 1 being 1, okay? But using the root in a totally pun form, okay? So this looks super general, but I'm just pointing out that there's not every equation is going to have a root, okay? Just because. And there's a simple one, x squared plus 1 equals 0. Doesn't have a root, okay? So x squared plus 1 does not have a root in our definition. Okay. I've got 1 minute, so I'm going to stop here because I don't want to mess up. We're going to recall what is a function that you learned. I don't know. When did we learn functions? 7th grade or something? I don't know. Okay. We're going to recall that, and then we're going to talk about continuity. And I'm going to need to define continuity in a way that it's not using calculus. So that should be fun. And then we'll go. We'll get the bisection algorithm. We'll start having a lot of fun. So thanks, everybody. We're setting ourselves up for some really, really cool stuff.